Hello YouTube. So today I'm going to be making a video explaining how I can get rays bending like this in an atmosphere which only varies as a function of elevation or height. This is a claim that I made on a stream with Anthony Riley. And of course, his argument was very simple. If you think about that, this gradient in the atmosphere being a bunch of layers of different varying index of refraction, because this horizontal ray is parallel, exactly parallel to all of those layers, it will never actually be incident on a layer and therefore get refracted up or down. Now, the reason why this argument is fallacious is because when you do this calculation in a continuous medium, not just layers of discrete changes in index of refraction, but really a truly continuous function, you can't use Snell's law anymore, right? Because these layers are infinitely thin. So you really have to be careful when doing this calculation. You really need to use the more sophisticated version of refraction called Fermat's principle. So in this video, I'm basically going to discuss how one derives Fermat's principle in the case of a generic case of a medium varying in the x and y direction in a two-dimensional plane like this. And then what I plan on doing after that is showing you that how the curvature of this ray, aka how much is it bending away from the horizontal, is directly dependent on the density gradient itself. So there's going to be a proportionality. So how much curvature the light ray has, this horizontal light ray has, is directly proportional to the density gradients. And I will show that the curvature is positive when you have a positive density gradient, aka when the density is increasing as a function of elevation. And the curvature is negative when you have a decreasing density gradient, aka the density is getting smaller as you increase in elevation. And this would explain how we get things like inferior mirages and stuff like that. So let's basically start out with Fermat's principle. So I made a little document here. So actually Wikipedia, let's go to Wikipedia first. So what Fermat's principle says is that the light path, the path that is taken by light is the path which is traversed in the least amount of time given the velocity inside that medium. So this leads to Snell's law in the case of two separate medium. In the case when you have a medium with a low density and a medium with a high density. And I will actually show you how you get straight lines in a homogeneous medium. But basically, this does not apply when you have a continuously varying medium, aka something where the medium is not just a sharp step between two different values, but actually a smooth, varying function of position. And basically what they do is they derive this equation here. So the time is just a sum over all of these individual path lengths, right? The integral is basically a fancy version of a sum over infinitesimal points. And basically what they do is they say, okay, in order to calculate the time that it takes to go from point A to point B in a medium, I have to do this integral here. Let's actually break this down a little bit more to see how one arrives at this expression, because it might be a little bit funky for people who have not done calculus. So what I want to do is I want to break up the trajectory of the light. So this is a generic curve, right? Because in principle, we're looking at any path the light ray can take, and we're trying to find the minimum one. So basically what I want to do is I want to find the total time. So I'm going to take this curve and I'm going to break it up into points. And these points are going to be made up of straight lines. And what I'm going to do is I'm going to make these line segments smaller and smaller until they perfectly follow the curvature of this curved path. But let's calculate the time that it takes to traverse one of these line segments. Now, so the time that it takes is just the distance traversed along the trajectory divided by the speed. Now here I'm not using v for velocity, I'm using v for speed, because speed is the magnitude of the velocity. And this velocity is not going to be constant. This velocity will depend on which line segment I look at, right? Because the index of refraction might vary in this xy plane. And so the velocity will depend on which line segment I look at. But for one line segment, I'm going to approximate this as a constant. And then when I take the limit as this goes to 0, I will definitely have a velocity point for each point in space. And that. So if I zoom in, now note that this triangle is extremely exaggerated just to show scale. When we do the limit, this triangle will basically become so small that you will be able to approximate this curve exactly. But for this big triangle, it's a right triangle, we can actually relate the displacement along this path to the displacement along the y and x direction. I call this dx and dy. So ds is just by Pythagoras' theorem, the sum of the squares and square rooted, right? Dx squared plus dy squared. Now, the next thing I want to do is I want to replace the velocity, right? The velocity is just the speed of light in a vacuum, which is denoted by c, divided by n. So, and this is cited by, I can cite this here. So n is c over v, and if I solve this for v, I get v is equal to c over n. And so 1 over v is just n over c, right, what I have here. Now, I'm specifically interested in finding y as a function of x. So I want y to be the elevation of the light ray to be the dependent variable, and I want x, the position along the trajectory, to be the dependent variable. And so what I'm going to do is I'm going to remove this dx from this square root, and I'm going to replace this with dy by dx. Now, for those of you who've actually taken calculus at some point, you'd recognize this as being the derivative of y with respect to x, and this will become important later on when we're actually doing the calculus of variations in order to find the minimum path length. But for now, we're just going to leave it just by this identity here. And so what we do is now we take, to find the time, we sum up all of the individual paths along from the initial x value to the final x value, which gives us an expression which looks like this. Now here, n is generically a function of both the horizontal position and the vertical position. And then we have this funny factor here, which is 1 plus dy over dx squared, square rooted, times dx. Now, in the case of a homogeneous medium, this n0, this function is just a constant. So it doesn't vary with space. And so I can pull it out of the integral, and you might be wondering why I pulled the 1 over c here, and this is basically just a property of integrals. So if I have a constant inside the integrand, I can pull it out of this integral because basically this is just scaling the entire sum here by a constant amount, and so these two are identities. And this is for any integral that you want to do. So I pull out the n0 and I pull out c. So you notice that this is just the velocity and this 1 over the velocity. And then we've got this funny expression here. Now, this expression here is very interesting. So if our hypothesis, if this makes sense, basically, not our hypothesis, if this makes sense, this should actually be just the straight up length of the curve, right? And fortunately for us, if I go to the Wikipedia page, calculate for arc length, this is exactly the expression that we get for calculating the length of a curve defined in the xy plane, where y is equal to f of x. And f has to be continuous, which just means, and differentiable, which just means that it has to be a smooth curve which doesn't have any breaks in it, which all of the light rays will have this property. And so basically we see that, okay, in a homogeneous medium, the time that it takes to go from xi to xf for a given trajectory of the light ray is just the arc length divided by the velocity in the medium. And so when we actually extremize this, when we find the minimum, clearly the trajectory which gives the minimum time is just a straight line. This is just plain Euclidean geometry. So, but what happens when we try to extremize this in the case where the n only varies as a function of height? And to understand this case, what we need to do is we need to use what is called calculus of variations. And they actually talk about this here. So in the Wikipedia page, they cite calculus of variations. So in the context of calculations of variations, this arc length here, which is proportional to the time, can be written as this strange d times s. And this d stands for the variation of this. And so what we're going to do is we're going to look at the calculus of variations of this particular function, this particular expression here. So let's go to calculus of variations page. So what is calculus of variations? For those of you who don't know, calculus of variations is a field of mathematical analysis which uses variations, which will be described here, small changes in functions and functionals, to find the maximum or minima of functionals. And functionals here are mappings from the set of functions to the real numbers. So a real number here is just any irrational number like 1, 2, 3, pi, e, it's just a number that for the layperson, this is just a number. It has, so does this satisfy the properties of a functional? Well, yes. I give this thing a y of x being the trajectory of the light ray, and I perform this integral, and out of this I get a time, right? So input is a function, output is a number. So this is exactly a functional. So this is something where I can actually use calculus of variations. Now notice here that I've changed the notation slightly. So y is a function of x, meaning y is the dependent variable, x is the independent variable. And here y prime is just the derivative with respect to x. I introduced the notation here to be consistent with the calculus of variations Wikipedia page. Now, interestingly enough, how one actually solves for the extremum, right, maximum or minimum, is via the Euler-Lagrange equations. And this basically tells us how to derive the Euler-Lagrange equations. You have a functional j of y, which is an integral of a function, which is a function of x, y of x, and y prime of x. Notice anything familiar here? This thing is a function of y of x, y prime of x, and indirectly x. And so they go through how you derive this, but they do the variation. And what you show is that and this is the fundamental lemma of calculus of variations, is that if this quantity is 0, this quantity here, now I know for a lot of people who have not seen calculus, this might be a bit confusing, but basically if I solve this equation here, then I found the extremum of this path. Now, there's an important caveat here. So the Euler-Lagrange equation is a necessary condition, but not a sufficient condition for an extremum. However, in the case of the identities that we are working on here, we can show that any Euler-Lagrange equation is also an extremum of the functional. So this is just basically saying that this is not the only condition that is required to make sure it's an extremum, but you can actually show that for this particular functional here, if we just do the Euler-Lagrange equations, it is perfectly fine. So they do an example here, which is very interesting. So this is our good old functional from before, the arc length. And what they actually use, damn it, where did it go? Calculus of variations. They actually use calculus of variations to derive the extremum, which is just a line. So they actually do this for the constant index of refraction in this segment here. And they show that using the Euler's principle, we get a straight line for the trajectory of the light. So that's actually pretty cool. But what we need to do is we need to do it for a more general case, not just a constant index of refraction, but we want to do it for this index of refraction, which is varying as a function of height. So in order to do that, in order to spare you guys a lot of the gory mathematical details, I'm going to go to a program called Mathematica. And Mathematica is a nice tool used by people in engineering and sciences, which deal a lot with, and also theoretical physics, and also experimental physics, depending on what your use cases are. But basically, it's a program which allows you to do mathematical manipulations symbolically without having to do pen and paper calculations. So the computer will actually do mathematical manipulations. It will not crunch numbers, it will actually crunch symbols. And so there's a nice package in Mathematica which is called variational methods, which basically provides a set of tools to exactly solve the problem that we're interested in solving. And so in this case, I'm going to be making use of the function Euler equations, which allows you to basically derive the Euler equations for a particular function, a particular Lagrangian, which is this L. So here you see our good old friend again, the line equation. And this basically shows you how you can use the Euler equations to show that you get a straight line path, right? So this is actually pretty cool. So let's apply it to our functional here. So I'm going to open up Mathematica, create a new document. So I need to import it. So let's do needs variational methods. So that imports it. So my Lagrangian is going to be n of y of x times the square root of 1 plus y prime of x squared. So in Mathematica, you use brackets to denote functions. And in this case, I print it out as traditional form so you can see that it looks exactly the same as what we see here. Actually, let's make this a little bit bigger. Okay, and notice here how this exactly matches this function here. So what I want to do is I want to find the Euler equations for y of x and x as my thing. And so let's print it out. So what this does is it takes the L, this L here, and it finds the Euler equation, which is a second order differential equation, to solve for the extremum path of this L. Now, actually, just for fun, let's just solve for, actually, no, we'll leave it for now. So what I'm particularly interested in is I want to solve for a differential equation which has the form y double prime, right? Here, double prime is the second derivative of our function. So prime is the first derivative. It's the rate of change of y. And y double prime is the second derivative, or the derivative of the first derivative. So what I want to do is I want to solve this equation for y double prime. And so to do that, I can use a method called solve, and I can say solve Euler equations for y double prime of x. And then let's do sole traditional form. So what this shows is that y, after doing, it's a very simple manipulation, but basically you say y double prime is equal to this thing here. So 1 y prime plus 1 times n prime of y divided by n. So n prime of y is the gradient of n, and n is just the function itself. So now this basically gives me an equation very similar to Newton's law of the motion of particles. This gives me an equation for the trajectory of light rays. So I can give it an initial angle or an initial derivative, and I can give it an initial position, and I can solve this equation, which is what I actually do numerically in my refraction calculator. But I'm interested in a claim that was made that is made by Anthony Riley, in particular that if you have a horizontal ray, it will not bend up or down. And to evaluate this claim, we have basically everything that we need. So it's clear that if I look out horizontally, my derivative is 0, right? The rate of change at that point is 0 because the slope is 0. The definition of horizontal is the first derivative is 0. But what does this equation tell us? It tells us that there is a relationship between the second derivative and the gradient of the index of refraction. So let's go to the definition of what curvature is. So curvature tells you how much a curve at a particular point is changing relative to its tangent. So if I have curvature, then that means that even though my curve might be flat, there's a tendency to move either up or down relative to the horizontal here. Now, there's a few different ways of defining curvature, but in particular, I'm interested in the case where we have a graph, right? Where we have y is equal to a function of x. I guess, again, y is our dependent variable, x is our independent variable. We can define the curvature, in this case I care about the sine curvature, is by taking the second derivative and dividing it by this combination of the first derivative. And so since we know that, well, let's just plug it in, right? Basically, this is what we want to calculate. And we know that any trajectory of light will obey this equation at any given point. And so let's just calculate what that is. So k is equal to y double prime of x divided by 1 plus y prime of x squared. And now I want to take my solution that I calculated and plug it into this equation here. So to do that, I just do this thing here and I do sol 1. Now the reason for this here is basically so that I don't get these weird brackets. And then let's do k just to see what it looks like. Oh, I forgot. This needs to be to the 3/2. Okay. So this tells us that this is what the curvature of a light ray is at any given point during the trajectory. So it is n prime over n times this square root of y prime squared plus 1. Now, I'm also interested in the horizontal ray, so I can say y prime of x goes to 0. And I'm left with the following expression. The signed curvature of the ray, how much it's going to deviate from horizontal, is given by n prime divided by n, or basically, going to my document here, for Fermat's principle, the the curvature is given by n prime over n, which is proportional to the gradient. So if I have a positive gradient, I have positive curvature. If I have a negative gradient, I have negative curvature. Now, if I plot this on a graph, and just a representative of that, k being positive is having a curve which goes like this, and k being negative is having a curve that goes like this. But don't take my word for it. The simplest function which has curvature given by k is the function that I'm writing down here. So f of x and k equals kx squared divided by 2. Now, how do I know this is a case? Well, let's calculate the curvature based on this formula. So k, so if I do, let's just say, actually this should be y. Let's do y prime. Oh, actually, sorry guys. I actually need to do y what is it doing? Okay. All right, let's see. So well, basically, all right, so if I just do d of k, I need to clear some variables. So d calculates the derivative of a function. So if I do d of kx squared divided by 2x, so going to copy this. If it would actually copy. Oh, actually, you know what? I can probably do this. I wonder if this will work. Ah, shoot. All right, well, y prime has to be equal to the derivative with respect to x, and y double prime goes to d of kx squared divided by 2x2. So this takes the derivative twice, and I should get something that looks like this. Now, this is a function of x, but in particular, I want to calculate the curvature at the point where x equals 0. And so what I'm going to do is then I'm going to do x goes to 0. Nope, I guess not. So this function has curvature k at x equals 0. So let's actually plot what that looks like just for the, so we can do manipulate, plot, kx squared divided by 2, x 0, 10. And then I'm going to manipulate the curvature. Yep. So As I change curvature to positive, it bends up. If I change curvature to negative, it curves down. So you can think about this as being the horizontal light ray and the direction that it travels after it leaves the observer being horizontal or vertical, right? So what I've basically demonstrated here is that Fermat's principle does make light rays bend even though they're going out horizontally. And it's perfectly consistent with the diagram that I have here. So in this case, the density gradient that I have the density gradient for the bottom 200 meters is positive. And so in that density gradient, because the density gradient is positive, the rays are being bent upward in accordance with Fermat's principle. So this basically concludes the broadcast. I hope everyone at least partially understood what the argument was. If you have any questions, obviously I will try to answer them in the comment section. And yeah, that's basically all I had to say. So thank you very much for listening to me, and I will hopefully be talking to you guys later on. Thank you. Bye.